and will just decay to empty space plus radiation. That's called the Hawking-Page phase transition. You don't see it by differentiating thermodynamic functions. It's not a local thermodynamic instability. It's not that there's a, if you look at a thermodynamic function, there's a direction where you can decrease the energy. You're looking at two completely different points in configuration space, and one has a lower energy than the other, so the system can jump from one to the other. So I'm going to look at rotating black holes, but let's take the charge to be zero. I'm looking at rotating black holes because we saw earlier that we had this critical point associated with rotating black holes, but that was attained at fixed angular momentum. Now, if you fix the angular momentum, the black hole cannot decay to empty space, because empty space doesn't have any angular momentum. The Hawking-Page phase transition is not for black holes with fixed angular momentum. It only manifests itself for black holes with fixed angular velocity. You can have empty space full of radiation with angular velocity. So this was what Hawking-Page showed, that if we look at the thermodynamic potential, there's no name for this potential in the textbooks. I'm not sure what they call it. It's like some sort of super Gibbs energy. It's like the Gibbs free energy, but there's order transform and everything. For anti-de Sitter space with radiation in it, if you know the back reaction of radiation is just zero, the black hole will be globally stable if its extended Gibbs energy is negative. And so there'll be a first order phase transition when the Gibbs energy of the black hole is zero. If the Gibbs energy of the black hole becomes greater than zero, then the black hole will just decay. So this is what the phase diagram looks like for a rotating black hole with fixed angular velocity. So again, I have pressure up this axis here and temperature along here. We have a line of first order phase transitions. This line goes on up to infinity. It never stops. The latent heat is increasing as we go up this line. And the wrong way around. The latent heat decreases as we go up this line. But you never get to a critical point. You have to go out to infinity before the latent heat vanishes. At any point that's not out at infinity, there's a non-zero latent heat across this line, and we have a phase transition, first order phase transition. So to the left of this line we have pure anti-de Sitter space with radiation, and to the right of the line the black hole is stable. So in this region here, the Gibbs energy of the black hole is negative, and in this region here the Gibbs energy of the black hole is positive. There's a technical point that you can't get below this blue line. Well, it depends on the physical situation, but if the angular momentum is too large, then anti-de Sitter space is rotating faster than the speed of light at infinity. So if the angular velocity is too large, then anti-de Sitter space is associated with speeds that are faster than light at infinity. So you don't want to do that. So that means that you can't go below this line. Because I don't think I've written it down, should have written it down, sorry. This pressure here is now measured in units of angular velocity. So this is P over omega squared. This is the pressure divided by the angular velocity squared. Sorry, P times omega squared. This is the pressure times the angular velocity squared. So as the angular velocity goes to zero, you can always come down to the origin here. So the position of this line is fixed by an angular velocity. But if you could cross this line, something very interesting happens. The latent heat of this first order phase transition diverges at this point. And what happens on this line here is that above this line, the Gibbs energy of the black hole is negative. Below this line, the Gibbs energy of the black hole just isn't defined. It becomes complex. So the Gibbs energy of the black hole is negative, and it decreases and decreases and decreases until you get to this point, and it just disappears. So what happens here is if you go from the black hole phase with negative Gibbs energy up to the anti-de Sitter phase with zero Gibbs energy, it's like a zeroth order phase transition. There's a jump. This line is determined by equating the Gibbs energy of the black hole to the Gibbs energy line in space. That's how you describe. That's how you obtain the line of phase transition. You equate the Gibbs energies on that line. Here, the Gibbs energy jumps. You have a first order transition if the Gibbs energies are equal, but its first derivative is not defined. If the Gibbs energies are equal and the first derivative is continuous, you have a second order phase transition. Here the Gibbs energies aren't even equal. So this could be called a zeroth order phase transition, if you like. It'll be associated with infinite latent heat. And they're actually, in a finite volume system, of course, the latent heat would be quite infinite. But there are examples of systems, and even the laboratory, where the Gibbs energy actually jumps across the phase transition, and they have been called zeroth order phase transitions.
Excuse me.
Yeah.
Is it possible to take flat filter in it?
Flat? You mean asymptotically flat?
Yes.
Or,
lambda goes to 0.
well, if lambda goes to 0, the pressure would be going to 0. So yes, you can certainly take that limit, and what happens then is that all black holes are unstable. Because well, actually, that's the local instability. I should think more carefully. Yeah, sorry. If lambda goes to 0, what happens is that this whole thing will just move down to the order, but the pressure would all be 0. So you can never get up here with lambda near 0. Lambda being 0 just means that you're on the line. Yes, you can take lambda to 0, but it's just a one-dimensional line that's expanded. But if lambda goes to 0, the angular velocity has to go to 0. You can't have non-zero angular velocity when lambda is 0, because otherwise things are rotating faster than light. Okay. So I hope I've tried to convey the fact that the thermodynamics of black holes is very rich. We see it's not the same as ordinary thermodynamics. It differs in some very important features, but almost many of the features that we're familiar with from ordinary thermodynamic systems are reflected in black holes, at least in principle. But in practice, you can't measure these things or see them. So there's a couple of comments here that I've already mentioned. I've written here the formula for latent heat explicitly as a function of temperature. So as we go up here, as you can see from this formula, as you go up this line here, the latent heat diverges linearly with temperature. And the denominator here being 0 is this one here. This latent heat diverges. So and you have this line of the critical point down here. Critical in the sense that you have to tune both the pressure and the temperature to hit this point. It's not critical in the sense that it's second order. The critical point and the second order phase transition are a priori independent things. Critical point. The definition of a critical point is you have to tune the pressure and the temperature to get to that point. And here we have a critical point where the latent heat actually diverges, so it's not a second order phase transition. It's more appropriately called a zeroth order phase transition. So we can see all of these phenomena in black hole diagrams, the phase space of black holes. Okay. Well, I've now, not only did it start 10 minutes late, I've now overrun by 10 minutes, so I apologize for that. I'll skip this and just throw up the conclusions, and thank you for your attention. Question or comments?
As you pointed out in your speech that you thought that the mass of the black hole is more like enthalpy than your just energy density. So that means that the sum of the mass is actually contributed by both the thing that make up this black hole, the thing that collapses, and as well as the vacuum energy in the vacuum. So, but we think that the vacuum energy or the cosmological concept, if we interpret them as the measure, as some energy, then it seems that the statement becomes that the temperature of the black hole is the combination is contributed by both the matter content that make up the black hole as well as the background. I mean,
well, I don't think you can break it up quite as simply as that. Certainly, I mean, what you see, the enthalpy is is a mixture, is a combination of the energy from the black hole and the vacuum energy. So you can think of that when the black hole is formed, then excluding a region of space from the exterior, and the vacuum energy associated with a region contributes to the black hole mass. But the temperature, I don't think you can say that the temperature is a combination of bits from the black hole and bits from the vacuum. All you can do is write down the enthalpy and differentiate it to get a temperature. And without looking at some kind of microscopic physics, which I have never done, I don't think you can necessarily disentangle that into different components. That would be my view. I don't know if that answers your question.
The thermodynamic valve, is it always plastic?
Excuse me?
The thermodynamic valve you define.
No, not always. It's negative for Taiwan spaces.
It's really
which
not
is an
likely
interesting.
to have a geometric
It has no geometric interpretation. Being negative for Taiwan spaces is not completely crazy. This is what Clifford Johnson did. If you imagine creating a Taiwan space, there's a, if you take an ordinary black hole with radial parameter R, when you make a Taiwan space, I don't know how much you know about this, but you replace R squared with a new parameter, rho squared, which is R squared plus n squared, where n is enough charge. Rho can go to 0 when R is when n is non-zero. So that corresponds to like having R squared being negative. So it's almost when you create a Taiwan space, it's almost as if you're removing volume. You're removing negative volume. So if you think of a process that could create a Taiwan space out of a flat metric, you have to remove negative volume in order to make the Taiwan space. So there is a kind of thermodynamic interpretation of negative volume in that sense. But that's the Taiwan case example certainly highlights the fact that this thermodynamic volume is not a geometric. It should not really be thought of as a geometric.
I'm ignorant of graph, so I don't know whether my question makes sense. You a couple of times mentioned ADS space. Is it possible to consider black holes in de Sitter space?
Yes. Now that's one of the slides that I jumped. De Sitter space is a little harder. There's a number of subtleties, things about de Sitter space that make it a little bit harder. There are two event horizons for a black hole in de Sitter space. There's a black hole event horizon and a cosmological event horizon. So there's two temperatures in general. So the system, you can't think of the system as being a thermodynamic equilibrium. That's one difficulty. Now you can just treat the two event horizons as being two different thermodynamic systems, if you wish. A second point is, I've been talking about the black hole mass, but for those of you who know about these things, it's actually not straightforward to define the black hole mass. The black hole mass I've been talking about in de Sitter space has a well-defined definition. It's kind of the analog of the ADM mass in flat space. I think, I'm not sure if it's got a name, but Heriot and Taiwan, I think, were the first people who defined the black hole mass in asymptotically de Sitter by using symmetry at asymptotic infinity. In de Sitter space, you can't go out to asymptotic infinity because, again, as you go through the cosmological horizon, the radial problem becomes timeline. So there's no ADM type mass for a black hole in de Sitter space. So even defining the mass of a black hole in de Sitter space is problematic. Nevertheless, there are definitions available. So there's some results here for de Sitter space. I've already mentioned the two event horizons. So there's two volumes of a black hole volume and a cosmological volume. These are both thermodynamic volumes. If you fix the cosmological volume, then the cosmological horizon entropy is maximized by Schwarzschild space-time. So the black hole is not rotating. And that's one result. If you take the difference of the two volumes, you subtract the black hole volume, the black hole thermodynamic volume, from the cosmological thermodynamic volume, you get something that really does look very like the geometric volume between the two horizons. one other result here is that if you fix the total volume, so that's the difference of the cosmological thermodynamic volume and the black hole thermodynamic volume, you fix the total volume, then the total entropy is minimized if there's no black hole. And I think these are quite intuitive results.
So, can I rephrase my questions? Actually, I get an understanding from your talk that I was wondering if we can add the contributions from the vacuum energy to the enthalpy of the black hole, then why not we add all the other contributions from other fields? For example, any other matter field into the enthalpy. So if this is not possible, then so I obtain a conclusion that maybe what's important is the contributions from geometry of the background. Say you interpret the cosmological concept as geometrical objects or concept other than matter fields, so that it's a different way of contributing the entropy through geometry, so that you need to take care of this contribution separately, and to add the PV into your entropy. Am I understanding correct?
Well, I don't know if I can say anything that would satisfy you, but what I would say is that this relates to this talk yesterday, that we don't know how to calculate the cosmological constant. But in some sense, the contributions from all the other matter fields are already in the cosmological constant.
Right.
So my answer to your question would be that we're already allowing for them somehow in a way that I can't explain. They're already lumped into the vacuum energy. And in terms of the thermodynamics of the black hole, all you need is the entropy and the pressure of the angular momentum of charge. These are the only four things that can ever contribute to the thermodynamics. So in terms of some kind of macroscopic thermodynamic description, all of this information in the other field is all lumped into these parameters. The solution of Einstein's equations is macro solution. Any other questions?
Well, Brian actually works on quantum Hall as well, but you're more than welcome to ask a question after.